Good afternoon. My name is Mas Balayan Amawan. For my matrix number is 211292542. I am from program AY31, awareness 3. So good afternoon to IR Dr. Zamri bin Hassan. Today I want to talk about Lab 2 dynamic response of second order system. So dynamic response of second order system. Here derive the transfer function of capacitor of this VOS over VS for the electrical network. So we show in figure below. So here is the figure, and for this left there is two sections. Section A is about to derive the transfer function of for the capacitor, and section B is consider the following second order closed loop system. So here is the solution for the section A. So here is the step, and the final answer is S over 0.1 S power of 2 plus 2S plus 50. So this is the graph at the Simulink, and by using MATLAB we can see this is the step graph for the step. So for the 2B, so here I have already put it aside uh, the Simulink. I built it. So for the first one, just put 15 and 15 over S squared plus 8S plus 16. So 8S plus 16 is 0.5. This time is 0. So we run it and see how it goes. So this is the graph for the first. The second one is the 16, but it's a little bit different in the middle, and plus 16. The second one is for this section B2 is 16 over S square plus 16. So here we will test it and see the graph. So this is the graph for the second one. So the third one is 16 over S square 5S plus 5S and plus 16. So okay, the graph for the third one. Okay. For the last one is 20. This is a little bit different. 20 plus 1 S squared plus 9S and plus 20. where we can get the step and visit map. So when we got the step, we did using the Simulink. So we just using the coding that have given. So this is the coding that I have tried here. So we put this here. So this is for the first one for the post zero. Here is the value for the post zero map for the first, and for this one, if we want to get the step, we just need to change. We just need to change the last one here. Change this to step. Enter it. Okay. Enter it. So this is for the step reason. Okay, here we need to the big take the rise time, settling time, isn't it? And the last one is steady state. Here we can see the steady state, rise time, rising time, when the value is 1. So I was display this one. So in the conclusion, how I get the justify and the configure. So for the step one, justify and comment. So here we can see when we calculate the denominator s squared plus s plus 16, the answer was equal to 1. Is critical damper. In order to consider a critical damper, the damper ratio is equal to 1. So means by for the first equation in 2b is critically damped. So the second one is 16 over s squared plus 16. So for the PZ map, the pose 0, here is the result for the pose 0, and this is result from the step. So when we calculate the answer was equal to 0, it means it's undamped, because in order to consider undamped, the damping ratio must equal to 0. Means by when it's over to 1, it's critically damped. When it's equal to 0, it's undamped. So the third one is 16 over s squared plus 5s plus 16. So the pose 0 is here. We can see the pose 0 is here. Little bit up for the tree, and in imaginary axis is little bit down tree. So here is the just step diagram for the step. So for this one, the answer was equal to 0.625, means that is below than 0, and is still category in undamped, even is 0.65. When we in the 0 point, we just put it in a 1, but it's still under the 0. Is mean by this function, this equation is undamped. So for the last one, using the 20 over s squared plus 9s plus 20. So the pose 0 is here, steady in the 0. And this is for the step. We can see the rising time, the rise time, so for function, and steady time. So here is the different, even is 1, but the equal, but in this denominator, the answer was 1.006. When it's more than 1, not equal to 1, is mean by is over them. So for the discussion in this study, we use an equation to analyze the step response of a system concentrating on the accumulating, the damping factors turn out to be an important variable. Critical damping for a rapid oscillation-free returning to the equilibrium is indicated by damping factor of 1. An undamped system that is proof to oscillation is indicated by a factor of 0. Whatever number between 0 and 1, if it is undamped, just like I tell before, even it's 0.9, 0.8 or 0.6 is still category in the undamped. Where a delay indicates of oscillation. Overtime relation with a delay equivalent written are indicated by damping factor greater than 1. Is mean by the last that we calculate is maybe 1.001, 1.002 or 1. Is over than 1. Is mean by is will be a undamped reaction. So this understanding help research and engineer activated and category system reaction for efficient design on and optimization. So in the conclusion, for in the summary, our work is efficiently employing and given equation to analysis the step response, just like we doing just now. We can see when the number is 0 is in below 0 is and when it's 1 equal to 1 is mean by critical them, but when it's greater than 1 it will category in situation of over them. Right. Provide the information about the behavior system effectively with the respects to the damping factor. The accuracy of our finding instruction strengthened by the assessment of limitation using application in engineering, mechanics, control system design, and other actuation domain. This knowledge advances our understanding of system dynamic on the basis of their finding. Future study could be ancient system performed for certain technical requirement. So this mean by not only for the this subject, but we still have many other of the subject that using the system, using this step and the work that we just do to analyze about the step response in the information and everything and so far. So this knowledge is very advantage for our outstanding